All right, chemistry, this is your video lecture for Chapter 4, Section 1, a first of a two-part lecture. We're starting to talk about the quantum model of the atom. Your objectives for this section, I want you to be able to discuss Louis de Broglie's role in the development of the quantum model of the atom. I want you to be able to compare and contrast the Bohr model of the atom with the quantum model of the atom. And then at the end, I want you to be able to explain how the Heisenberg uncertainty principle and the Schrodinger wave equation led to the idea of atomic orbitals. Notice that word is orbitals, not orbits, in the same way that the Bohr model of the atom suggests. We're also going to introduce quantum numbers. There are 4 of them, and you need to be able to describe their significance, as well as relating the number of sublevels corresponding to each of the atom's main energy levels, the number of orbitals per sublevel, and the number of orbitals per main energy level. Let's get started. Last section we talked about the fact that light exhibits both wave-like and particle-like properties. We are going to now extend that idea to electrons, and that started with Louis de Broglie, a French scientist, when he first suggested that electrons be considered waves confined to a space around an atomic nucleus. It followed, naturally, that the electron waves could only exist at specific frequencies because you cannot complete a particular wavelength in a set amount of space if you get outside of that particular frequency. According to the relationship, energy is equal to Planck's constant multiplied by the frequency of a photon. These frequencies corresponded to specific energies. These are the quantized energies that Niels Bohr referred to in his model. Moving forward, electrons, like light waves, can be bent or diffracted. And diffraction refers to the bending of a wave as it passes by the edge of an object or through a small opening. Electron beams, like waves, can interfere with one another. Interference occurs when waves overlap.
In 1924, Louis de Broglie proposed that electrons, like light, had properties of both particles and waves. De Broglie suggested that electrons be considered waves confined to the space around an atomic nucleus. De Broglie suggested that an electron would have a characteristic wavelength equal to Planck's constant divided by the momentum of the particle. It followed that the electron waves could exist only at specific frequencies equal to energy divided by Planck's constant. These frequencies corresponded to specific energies, the quantized energies of Bohr's orbits. 3 years after de Broglie's proposal, C.J. Davison and L. Germer discovered that electrons can be diffracted by a single crystal of nickel. This important discovery provided the first experimental confirmation of de Broglie's theory.
So let's see how we're doing so far. Only the wave theory of light offers an explanation for the ability of light to exhibit interference, reflection, photoelectric emission, or the intensity of radiation. Correct answer is interference. Interference is a property of wave-like objects. The photon or particle model of the light is more appropriate than the wave model in explaining interference, refraction, polarization, or the photoelectric effect. The correct answer is the photoelectric effect. Now we're moving on to the Heisenberg uncertainty principle. German physicist Werner Heisenberg proposed that any attempt to locate a specific electron with a photon knocks the electron off of its course. The Heisenberg uncertainty principle states that it is impossible to determine simultaneously both the position and velocity of an electron or any other particle.
Today, I'm doing an experiment that demonstrates Heisenberg's uncertainty principle. So here I have a green laser, and I'm firing it down towards the front of the room through a narrow slit. Now that slit can be adjusted so it could be made narrower or wider. And the laser spot is projected onto a screen behind it. So what do you think is going to happen to this spot on the screen as I narrow the slit? Well, let's have a look. where you see exactly what you'd expect. The spot gets narrower and narrower. The sides are getting cut off by the slit. Makes complete sense. And if you stop there, you would never realize that Heisenberg's uncertainty principle is at work. But if you keep going, something strange happens. As you make the slit even narrower, the spot starts to spread out. Isn't that incredible? You're making the slit narrower, and yet the spot on the wall is getting wider. The narrower you make it, the wider that spot on the wall becomes. To understand this, we have to look at Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is normally written as delta x delta p is greater than or equal to h on 4 pi. So what does this mean? Well, it's about the position and the momentum of a particle. So x is the position of the particle and p is its momentum. So delta x is the uncertainty in position and delta p is the uncertainty in the momentum. Now, if you multiply those two quantities together, they must always be greater than or equal to h on 4 pi. Now, h is Planck's constant, and that deserves a video all to itself, like this one by 60 symbols. But for our purposes, it's just a very small number. So in our everyday lives, we don't come up against this uncertainty relation because everything is much, much bigger than h. But as we narrowed the slit, we were decreasing delta x for those photons. So we were getting more and more precise about where the photons were passing through that slit. And at a certain point, you come to this limit, so that if you narrow this any further, you're going to break this uncertainty relationship. So what needs to happen is the uncertainty in momentum needs to go up. I should specify this is uncertainty in momentum in the x direction, in the horizontal direction. So if before photons were going perfectly straight, now they must veer off to the left or to the right to ensure that we don't break Heisenberg's uncertainty relation. And the more you decrease your uncertainty in position, the more narrow you make that slit, the more the uncertainty in momentum has to go up. And so if these photons are going to the left and the right, that's going to produce a much wider beam. It's really, really non-intuitive, but it's the way the world works.
Moving on to the Schrödinger wave equation. In 1926, Austrian physicist Erwin Schrödinger developed an equation that treated electrons and atoms the exact same way you treat waves. Together with the Heisenberg uncertainty principle, the Schrödinger wave equation laid the foundation for modern quantum theory. Now, quantum theory describes mathematically the wave properties of electrons and other very small particles, and the emphasis here is on very, very small particles. Electrons do not travel around the nucleus in neat orbits, as Bohr had postulated. Instead, they exist in certain regions called orbitals. An orbital is a three-dimensional region around the nucleus that indicates the probable location of an electron.
Is it possible for an electron to be two places at once? Or for a cat to be both alive and dead at the same time? According to quantum mechanics, both scenarios are possible. And at the heart of this conceptual dilemma lies the wave function, the mathematical formula that we use to describe quantum objects. To see the wave function at work, let's take the case of an electron shooting out of the back of a cathode ray tube, a device found in the back of old-fashioned TVs. The wave function for this electron is just a description of where the electron is and what it's doing. For example, how fast it's going. To predict where the electron will be in the future, you just plug the wave function into Schrödinger's wave equation, the quantum equivalent of Newton's laws of motion. But here's where it gets tricky. The wave function isn't a regular number. It's a complex function that relies on imaginary numbers, such as the square root of -1. And it gets even worse. The wave function can only give you a statistical prediction about where the electron will be in the future. It's a statement about probabilities, nothing more. If you took two electrons with the exact same wave function and looked to see where they are, you might find that one is over here and the other is over here. And worse yet, once you observe an electron, detecting it in this place and not in this place, the wave function immediately and irreversibly changes. Physicists say that it collapses from a broad range of possibilities to one specific answer. Think about that for a second. The act of measuring the electron is what gives it its position. And this brings us back to the cat that's both alive and dead at the same time. As it's usually told, a cat and a vial of poison are sealed into a box. Then, a quantum event happens with a probability of 50% that breaks or does not break the vial of poison and kills or does not kill the cat. So is the cat still breathing? The wave function reflects both possibilities. In the standard interpretation of quantum mechanics, both possibilities are real. The cat is truly both alive and dead until an observer opens up the box. At this point, the kitty collapses into either an alive or a dead state. This is absurd, of course. Cats can't be both alive and dead at the same time. So how do we get out of this paradox? One of two ways. Either the wave function doesn't really exist, it's just a reflection of our knowledge, or the cats are both alive and dead, but in two parallel universes.
All right, let's check to see how we're doing. Interference and diffraction, things we mentioned earlier in the presentation, can be explained by the wave theory only, the particle theory only, both A and B, or none of the above. The correct answer is wave theory only. Interference and diffraction refer to waves, not particles. Louis de Broglie was able to conclude that electrons also behave as waves because Bohr's model came to that conclusion as well. Waves in a confined space have certain frequencies. Line emission spectra show certain frequencies, or they reminded him of a guitar string. Correct answer is B. With regard to de Broglie specifically, his idea was that waves are confined to certain spaces and therefore can only have certain frequencies. Heisenberg's uncertainty principle states that you cannot know the location of an electron, you cannot know the momentum of an electron, you can only know one if you know the other, you can never know one and the other simultaneously. Correct answer is D. That's where we're going to leave off for today. We'll pick up the second part of this lecture next time. I will see you next period.